Okay, here we are with another video on capacitors, and this time we're going to have a look at another question. So here we go. Okay, so we've got a question here on series and parallel capacitors and working out the capacitance of these combinations. All right, so the first combination we're going to have a look at is obviously this one here that you can see. So we're going to look at this one first, and obviously this one, and then finally this one. Okay, now this one here, they're in series, they're in parallel. So those capacitors are in parallel. So the first thing you need to understand is that in parallel, the capacitance, the total capacitance is just equals the capacitance of each capacitor added together. Okay, so the total capacitance here is just going to be 2 plus 4 plus 8. All right, so in total that's going to be 14, and obviously that's picofarads. All right, so that's the first one done. Now the second one, this one here, the capacitors are in series, and if they're in series, we combine them like this. Okay, so the reciprocal of the total capacitance is equal to the reciprocal of each of the capacitors added together. So that's going to give us 1 over 2 plus 1 over 4 plus 1 over 8. Okay, and we can then deal with that, and we can make sure that they're all over 8. So we can say here that the total capacitance is equal to 4 over 8. So we're just multiplying the top and bottom there by 4 of that first fraction, plus 2 over 8. So we're going to multiply the top and bottom by 2, plus 1 over 8. So in total now that makes 4 plus 2 plus 1. So that's 7 over 8. And therefore the total capacitance is equal to 8 over 7. Okay, and that as a fraction is going to be 1.14, and that is picofarads. Okay, so 1.14 picofarads. Right, so let's have a look at the third one now. So if we just clear this page, we're going to have a look at this one now. Okay, so the first thing is these two are in series, so we're going to combine those together. And when we combine those together, we do that. So let's just get rid of that, and we'll call this one number 3 now, just for convenience. Okay, so we're going to do the combined capacitance of those two capacitors here is equal to 1 over 2 plus 1 over 4. Okay, so that's equal to 2 over 4 plus 1 over 4, which is equal to 3 over 4. So therefore, the total capacitance is equal to 4 over 3, which is obviously 1.3 recurring. Okay, so that's picofarads. Now, what we've essentially got now is if we were to redraw this capacitance, or this capacitor, sorry, we've got, whoops, let me just redo that. Just getting used to this new thing. So we've now got one capacitor like that, and then we've got another one like this. So they're basically now two capacitors in parallel. So this one's 1.3 picofarads, and this one's 8 picofarads. So to get the final total capacitance, we just do we're just going to do 1.3 plus 8, because when you have capacitors in parallel like this, you just add the capacitance together to get the total capacitance. So that's 9.3 picofarads. All right, so there we go. That's that bit done. So if we clear the page, and we'll move on to the next question. So it now says you've got a laboratory technician, and they need to make a capacitor that's got a capacitance of 2.7 microfarads, and it tells you the various bits of information about this capacitor. Okay, so we know that we need a capacitor of 2.7 times 10 to the minus 6 farads. We know the area of this capacitor because it tells you that it's a square sheet, so it's a square sheet of aluminium. Whoops, that is absolutely terrible, apologies. So it's a square sheet of aluminium, okay, and it tells you that the sides are 42 centimeters, okay. So therefore the area is going to be 42 times 10 to the minus 2 times 42, whoops, times 10 to the minus 2, okay, and that's going to give us 0.176 meters squared. And then we can just use the equation C equals epsilon naught A over D. And we're going to work out the distance between the capacitor plates. So what we're doing here is we've been asked to determine whether or not it's realistic for Michael to produce a capacitor of capacitance 2.7 microfarads using these two sheets of aluminium with no dielectric, okay? So is it realistic? Well, to find out if it's realistic, we're going to work out what the distance between the plates would need to be. So to do that, we're going to do, it's going to be epsilon naught A over C. So that's going to be 8.85 times 10 to the minus 12, because that's the permittivity of free space, multiplied by 0.176, because that's the area that we just calculated. And then we're going to divide that by 2.7 times 10 to the minus 6, because that's the capacitance that we need. And that comes out then as a distance of 5.77 times 10 to the minus 7 meters, which is also equal to 5.77 times 10 to the minus 4 millimeters. So clearly that's a ridiculously small distance between the capacitor plates. Way less than a millimeter. Okay, and that means that it's going to be they're going to need to be too close together to actually make a capacitor, so it's unrealistic. Okay, so we can say that it's unrealistic. Whoops, might need to spell that. Okay, so unrealistic. Okay, so the final bit of this question then is just to state what happens to the capacitance of a parallel plate capacitor when a dielectric is placed between the plates. And the answer here is it will simply increase. It will just increase the capacitance. Okay, so there we go.